Hello and welcome to further mathematical induction as part of the Extension 2 course. Before we actually get into further mathematical induction in the second part of this topic, we are going to review what mathematical induction actually is. We'll start with an analogy that I like to use for mathematical induction before stating the 3 steps required, and then we'll jump into 2 different examples. So let's jump into this analogy now. I want you to imagine a whole lot of dominoes. Okay, so we've got our dominoes set up with our first one here. This is our number 1 domino, and the lineup is just heading off forever. Now we've all seen those videos where you push the first domino and then they just knock into each other and they go off, and some really cool patterns and stuff. We'll keep it simple. We've just got a nice straight line. Now, how do we know that once we start this process that all the dominoes will indeed fall over? Well, if we can go to some generalized domino, so the kth domino, and if we assume that that will fall over, and then we can prove that the very next domino will fall over, so the k+1 domino. If we can prove that, then the very act of showing this first domino falls, coupled with this, is enough to prove that they'll all fall. So when the first domino falls, n=1, then because of this, the second domino will fall, because 1 + 1 is 2. But then if the second domino falls, then the third domino must fall, and so on. So this is an analogy for the process of mathematical induction. So let Pn be the proposition for all n that belongs to the set of natural numbers. And to use mathematical induction to prove this proposition, we go through 3 formal steps. Step 1 is to prove true for n=1. So this is our first domino. If we can prove that the first domino falls, then we're on our way. Now, must note that sometimes it's not actually n=1, it's just the first natural number that applies to a specific question, but generally speaking, it is. Step 2, assume true for n=k. So this is that generalized domino, the kth domino. And because n has to be a natural number, then k also belongs to the set of natural numbers. Alright, and finally, step 3. Prove true for n=k+1. So this is that domino that's following the kth domino. Now, when we do step 3, and this is by far where the most heavy lifting happens in the mathematical induction process, when we do this step, we need to use step 2 to help us. And we'll see how to do that in the examples that are following shortly. When you've completed steps 1, 2, and 3, then it's convention to finish off with a conclusion. And while it's up to you what to write in your conclusion, you're basically saying that by the process of mathematical induction, the proposition or the statement is true for all integers greater than or equal to 1, or wherever you start at. Okay, let's get into our first example, which is dealing with sums or series. Prove the following true for all positive integers. So our proposition is 2 + 4 + 6 and so on plus 2n equal to n outside of n+1. So we have a series here on the left hand side that'll get bigger as we go further and further along with different values of n, and we've got to prove that that's always going to be equal to this right hand side, n outside of n+1. So step 1, prove true for n=1, which is the smallest value of n in this particular case. So that means our left hand side series is not going to be very long. In fact, it's just going to be one term, the very first term. 2 lots of n or 2 lots of 1 is just 2. And what about the right hand side? So the right hand side is this n outside of n plus 1, and we are just considering n equal to 1, so let's substitute that in. And what do we get? Well, 1 plus 1 is 2, and 1 lot of 2 is 2. So we have that our left hand side and right hand side are equal. So we would just provide a brief little statement for step 1, that therefore the proposition is true for n equals 1. So it's like our first domino has just been knocked over. In step 2, we assume true for n equals k. So we take the original question, right, so that series on the left hand side, but we only go to the kth value. So we replace n with k. And the right hand side, likewise, instead of n outside of n plus 1, we've now got k outside of k plus 1. So that's step 2 done. And now on to the crux of the process. Step 3. Prove true for n equals k plus 1. So I always like to write out what I'm trying to prove, first of all. The textbook sometimes uses RTP, required to prove. So we've got this series on the left, and we're now going up to k plus 1. Right, but it's a good idea to still include the kth term, right? So 2 lots of k. And then our next one is 2 lots of k plus 1. So make sure you use your brackets here. And on the right hand side, we are now replacing k with k plus 1. So we have k plus 1 outside of, this is going to be replaced with k plus 1, and then we add on another one. So k plus 2. Okay, so this is what we are trying to prove, this line here. So let's start with our left hand side. And when we look at the left hand side, we notice that the first k terms, we can perform a substitution here. So if we're looking at these first k terms, they can be replaced with k outside of k plus 1 from back here in step 2. So this is what I meant previously when I said that we use the assumption from step 2 to help us in step 3. Now we still have this bit here, 2 outside of k plus 1. Now whenever we perform this step where we make the substitution, it's a good idea to state what we've done. So using step 2. Now our aim is to manipulate this so that it looks like our right hand side, k plus 1 outside of k plus 2. So expanding, we get k squared plus k, and in our second expansion we get 2k plus 2. Combining like terms, we get 3k in the middle. And when we look at this, we can see that it factorizes nicely into k plus 1 times k plus 2. And that is our right hand side. So we can state that and then write a brief little conclusion. So therefore, true for n equals k plus 1. And to wrap up, we would then write our conclusion. Okay, so something along the lines of, by the process of mathematical induction, the proposition is true for all n that belongs to the set of natural numbers. Okay, example 2. This example is what's classed as a proof of divisibility question. So we need to prove the following proposition is true for all positive integers. The proposition is 5 to the power of n minus 1 is divisible by 4. So whenever we're considering questions like this, we need to link divisibility and factors or multiplication. So if something is divisible by a certain number, in this case 4, then that means that 4 will divide nicely into this term. So there will be 4 times some other integer. So let's go through the steps and see what I mean. Step 1, prove true for n equals 1. So if we start with 5 to the power of 1 and subtract 1, well, that's just 5 take away 1, and we know that that's 4. And clearly 4 is divisible by 4. So we'll just state that. So we're all good there. We can say that the proposition is true for n equals 1. Step 2 is where we assume true for n equals k. For these divisibility type questions, we need to set them up in a unique way. So we can replace n with k, just like before. But in order to say that this is divisible by 4, we write that it is equal to 4 times some other natural number. Okay, so we would just state that, where p is some other natural number. Because if we have 4 times some natural number, whatever it is, then that means 5 to the power of k minus 1 must be divisible by 4. So that's how we set up step 2. Step 3, we need to prove true for n equals k plus 1. Let's start by writing what we're required to prove. And this time we're replacing n with k plus 1. And likewise, we want this to be divisible by 4. So we're going to write it as 4 times some other natural number. In this case, call it q. So once again, just clarify that q must be a natural number. Okay, so let's start with the left-hand side. Remember, we want to use step 2. So how can we take this 5 to the power of k plus 1 and somehow get something similar to what we see in step 2? Well, notice we've got 5 to the power of k. So how can we break 5 to the power of k plus 1 up into something involving 5k? Well, this is where we use our index laws in reverse. Remember, we know that some a to the m multiplied by some a to the n, because they have the common base, we would just add the powers. So if we go in reverse, then we can split something up where there's an addition of powers. So keeping our common base of 5, we can have 5 to the k, and then that is multiplied by 5 to the power of 1. So notice if we did combine these, that would give us 5 to the power of k plus 1 as above. And then we've got our minus 1 still tagged on the end there. What this allows us to do is to now perform a substitution. Now, we would need to rearrange step 2 first of all. Okay, so rearranging step 2, we get the following. 5 to the power of k is equal to 4p plus 1. And so that is what we can now substitute in here in our second line of working. So we'll replace 5 to the power of k with 4p plus 1, and that's multiplied by 5. And we have our minus 1. Now, whenever we do this, remember, it's good to write that we're using step 2. Now, remember, our aim is to show that this left-hand side is divisible by 4. So we need to keep manipulating this left-hand side until we can drag out 4 as some common factor. So let's expand the brackets here. You get 20p plus 5. Then we still have our minus 1. And when we simplify, we see that this is 20p plus 4. And now we can drag out 4 as a common factor. And we can just call this 4q. Right, so that's what we were after. That's our right-hand side that we were after. So in this case, it happens that whatever our p value is, q will be 5 lots of p plus 1. That's not really important, but just a little link between p and q. And so we have completed step 3. So it's true for n equals k plus 1. And once again, you could finish off with a concluding statement. Alright, so that finishes our second example for this review lesson. All the best with the exercise work.